roughly equal to that. And this derivation, this entire derivation, is equation 4. Okay, there's one more approximation, and that is, so let's look back at our expression, which was 2a sine pi f d1 by c2 over c cos 2 pi f ct 2 pi f t plus theta r. Here's my phase term, there's my signal term. This I can substitute approximately equal to 2a sine pi f d1 minus d2 is roughly equal to that. So minus pi f minus 2 pi f HTHR divided by dc. Cos 2 pi f t plus theta r. One more approximation. If u is approximately equal to 0, or if u goes to 0, u is very close to 0, sine u is approximately equal to u. So this expression is approximately equal to 2a sine, excuse me, I dropped the sign, minus 2 pi f HTHR over dc cos 2 pi f t plus theta r. And this derivation is equation 5. Okay, what is interesting about this expression? What's interesting is the following. A is the signal strength in each path, and that should be decaying with the free space loss, which is 1 over d squared. Excuse me, the power should be decaying with the free space loss, so A should be decaying as 1 over d. So A is big O 1 over d. Now this term contains, well, what are these things? 2 is a constant, minus is a constant, pi is a constant, f is a constant, HTHR, constant, speed of light is a constant. D is a function of the distance from the transmitter to the receiver. So this expression here is order 1 over d as well. And here's our signal. So now, our amplitude terms, so taken together, these amplitude terms are order 1 over d squared, which means power is what? Power is the square of amplitude, so how does power decay with d? It's 1 over d to the 4th. So I take this and square it, I get 1 over d to the 4th.
Excuse me, Professor?
Yes?
How is d squared responding to A? Like, I didn't get that last part.
Okay, so we have antenna. So I said the strength of each path, I just represented that by the coefficient A sine 2 pi f t. So A is from the perspective of the receiver. But we know that if this were free space and there was no second path, because that wavefront is expanding and the distribution of the wavefront is basically the surface area of that sphere, and that expands as 1 over d squared, we can argue that the amplitude decays as 1 over d. So in other words, if I move away from the antenna, the power will decay as 1 over d squared. Amplitude is the square root of the power. So the amplitude will decay as 1 over d. Make sense?
Yeah, but we have got 1 over d squared for A, and you said like for power it's 1 over d for, whereas in the equation we have only 1 over d.
So this is 1 over d. I'm arguing that A is 1 over d.
Yeah.
And I'm arguing that this is also 1 over d.
Oh, okay.
And if I multiply them together, I get 1 over d squared. So power decays as order 1 over d to the fourth. So the path loss exponent is 4. Okay, so this is a neat application of multipath propagation. It shows how multipath propagation can really hurt. However, the application of this is limited. So this only really works if the Earth is flat and a perfect conductor. So if Earth is flat, then we have that nice two-path model. If Earth is a perfect conductor, then we have r equals -1, which we might not have otherwise. Is there a question in the back?
When you say Earth is flat, you mean like the ground itself, and that's a specific area?
Yeah, so I don't mean like the world is flat. I mean relatively flat from the transmitter to the receiver.
Right.
Like over hundreds of meters.
So I mean, it's just near the webs.
Well, where would it work? Where is Earth relatively flat and a pretty good conductor?
Downtown?
The ocean. The ocean. So this is pretty good. Pretty good over seawater.
How much office is like some farm area?
It turns out that over Earth, like over soil, Earth is a relatively poor conductor, and the path loss exponent is usually pretty close to 2. The path loss exponent is usually close to 2 as long as you have a direct line of sight from the antenna to the receiver, or from the transmitter to the receiver. And in fact, let me write that down. So dry ground path loss is close to 2 as long as a line of sight exists. So I'm showing you this firstly to give you, like I said, to give you an interesting example of multipath. Secondly, this is applicable, so ships at sea experience this. This is a big deal for the design of sea-skimming missiles. When they're homing in on a ship, their radar signals actually decay very rapidly, very close to the sea. But on dry ground, there's no analysis to show this. This has been found by experiment that path loss exponent is usually pretty close to 2 over dry ground. Yes.
So the D2 path that we had, that is always unique.
Yes. So it's because so there's the direct path. It's unique because that angle has to be the same as that angle. So that's all. This second path is always unique.
So we could just get rid of that particular point.
Which point?
I mean, if you could make sure that that one particular point
What
is
do you mean
not
here? Yeah, so if these two antennas were fixed, yeah, you could go to this particular point and